Okay. Today, these are the topics for today's class. In the first topic, I present two basic properties about determinant. Second topic, I present more examples about determinants. And in the third topic, some applications about determinants. And in the last topic, if I still have time, then we turn to study section 5.1. 5.1 about eigenvalues and eigenvectors of a square matrix. Take a review. Take a review about how to compute a determinant. Let A be a square matrix n by n. Determinants are for square matrices. For rectangular matrices, we don't have determinants. Suppose A is this n by n matrix. Then how to compute the determinant of this matrix? How to compute determinants of this matrix? Two approaches. Number one, by expansions. We can expand the determinant of this matrix across any row, say across row I. The formula is AI1 times CI1 plus AI2, the second entry, times CI2, and so on. The last entry is AIN times CIN. What is C? Okay, the formula for C is Cij is -1. The power is I plus j. Then times determinant of capital Aij. Capital Aij is a matrix. How to get this matrix? Delete row I. Delete column j. Then we get capital Aij. Cij, the definition is this number. Determinant is a number, this number. Okay. Yeah, this formula, we call it expand a determinant across row I. And also you can expand the determinant down any column. Say down column J. The formula is this. The first entry, A1J times C1J plus second entry, A2J times C2J, and so on. The last entry, ANJ times CNJ. Yeah. The results are equal. Expanding this determinant across row I and expanding the determinant down column J. The results are equal. This is one approach to compute a determinant. The second approach to compute a determinant is reduce the determinant to epsilon form. Okay. Yeah, here, review number 2. we can compute a determinant by reducing it to an epsilon form. Epsilon form. Epsilon form is an upper triangular form. Determinant of an upper triangular matrix is just the product of the main diagonal entries. About reducing a determinant to an epsilon form, there are some formulas. Okay, formula 1. When you interchange two rows, remember, add a minus sign. Okay, say A11, A12, A1J, A1N. A1N. Say I interchange row I and row J. Row I1, I2, IN. Row J, J1, J2, JN. The last row, AN1, AN2, ANN. Determinant. We use vertical lines on the both sides. Vertical line means determinant. It is a number. Now I interchange row I and row J. Here is a row J. And row I here. The last row still AN1, AN2, ANN, determinant. When what is the relation between these two numbers? Add a minus sign. When you interchange two rows, add a minus sign. This is a formula 1. Formula 2. Suppose some row of the determinant is C times AI1, C times A12, AI2, C times AIN. C is a common factor of the entries on row I. AN1, AN2, ANN. Yeah. Okay. Now, what is the relation of this determinant with the original determinant? A11, A12, A1N. Original determinant AI1, AI2, AIN, AN1, AN2, ANN. What is a relation between these two numbers? It turns out that you can take out the C on row I. C, yeah, this number is equal to C times this number. Formula 2 about reducing a determinant to an epsilon form. Formula 3, Number 3. Some number times some row add to another row. Yeah. A11, A12, A1N, AI1, AI2, AIN, AJ1, J2, JN, AN1, AN2, ANN, determinant. Now I perform the operation. Some number, this number, some number times row I plus row J. Then put the result in row J. Yeah. Some number times row I, then add to row J. It turns out that this operation doesn't change the value of the determinant. Yeah. A11, A12, A1N. This operation doesn't change row I. So let me copy row I here. Right. Now, row J is changed. C times row I add to row J. So row J becomes AJ1 plus CAI1. Then the second entry on row J, C times this entry add to this entry. So AJ2 plus CAI2, and so on. C times this entry add to this entry, AJN plus CAIN. Only row J is changed by this operation. So the bottom row still the same. Yeah, this operation doesn't change the value of the determinant. This number and this number, they are equal. So this is a review about how to compute a determinant. Number 1, you can compute a determinant by expansions. Number 2, you can compute a determinant by reducing the determinant to an epsilon form. If you ask me which approach is better, I prefer the second approach. Reduce a determinant to an epsilon form. Okay. Now, this is our review about the computation of a determinant. Let me show you one example. Say, take a look at this example. Example 1. And let A be an n by n matrix, square matrix. This matrix has n rows and n columns. Let A be an n by n matrix, and let C be a scalar, a number. Okay. Then C times matrix A. Then take determinant. What is the formula? It turns out that it is C to power n times determinant of A. How to see this formula? Yeah, solution is how to see this formula. Okay, now in detail, let me write down the matrix A in detail. Let matrix A be A11, A12, A1N. Second row, A21, A22, A2N, A31, A32, A3N, and so on. AN1, AN2, ANN. Matrix, yeah. For a matrix, we use a square brackets on the both sides. Okay, then C times A. What is a number times a matrix? The number times all the entries. So C times A is C times A11. C times A12. C A1N. C A21. C A22. C A2N times all the entries. F3N. C times AN1. AN2. Yeah, this is 2. C times ANN, right? This is a C times A. It is a matrix. Now I compute determinant on C times A. Yeah. By formula here. This formula, C times rho I can take out C. So by the formula, for the first row, I take out C. Then we get A11, A12, A1N. In this equation, I only take out the C in the first row. Second row, still C times A21, C times A22, C times A2N. Third row, still the other rows not change. 3N. C times AN1, C times AN2, C times ANN. Yeah. This number is equal to C times this number. Now, for this determinant, look at the second row. C is a common factor. I can take out C from the second row. Then take out C. Then C times C. C squared. And on the second row, take out the number C. The third row, not change. C times N1, C times N2, C times NN. Yeah. Okay, now on the third row, let me take out the number C. Take out the number C. Yeah, third row, take out the number C. Okay, take out number C. Now C squared times C is C to the third. C to the third. On the fourth row, take out the number C. Then we have C to the fourth. Okay, continue this process until all the C's are taken out. Then we get Cn. Now, the last row also take out C. Then we have this formula. Yeah. A number times a matrix, then take determinant is C to the n. N is the size of the matrix times the determinant of matrix A. We have this formula. Yeah. Now let's turn to topic one. Two basic properties about determinants. Which two basic properties? Topic one. Okay. Basic properties. We often use these two properties. Number one, here assume let A and B both n by n, same size and square. A times B. Then determinant, it is a number. It is equal to determinant of A, a number, times determinant of B. Property number one, we often use this property. Determinant of a product is product of determinant. Yeah. Good. Very powerful property. Property B. A square matrix. Determinant is equal to A. Take transpose. Draw a line along the diagonal matrix, then rotate the matrix to get A transpose. Determinant. It turns out that take determinant on a square matrix doesn't change the value of the determinant. Yeah, we often use these two basic properties. Now, let me show you examples about these two properties. Example one, under this topic. So that if A is invertible, the matrix A has inverse, then A inverse determinant is equal to 1 over this number. Determinant is a number. How to see this equation? How? Solution. How to see this equation? Because A is inverse, so A times inverse is equal to identity matrix. Now I take determinant on the both sides of this equation. Now take the determinant. Determinant on the left side. Determinant on the right side. Identity matrix is a upper triangular matrix. The determinant of an identity matrix is the product of the main diagonal entries of I. Main diagonal entries of I all are ones. So determinant of identity matrix is 1. Yeah. This is 1. Number one. All right. Now on the left side, I apply this property, okay, on the left side. Determinant of a product is product of determinants. Okay. Then, therefore, determinant is a number. A here is invertible. This number is non-zero. So I can move this non-zero number to the right-hand side. So A inverse determinant is equal to 1 over this non-zero number. So done. If A is invertible, then the determinant of A inverse is 1 over the determinant of A. Yeah. This is example 1. Now, second example. Example 2. Example 2. Let A and P be n by n squared. Okay. And P is invertible. P has an inverse. Okay. Then so that determinant of P times A times P inverse. Here I assume P has inverse is equal to determinant of A. How to see this equation? Now, solution. Okay. Now, P times A times P inverse determinant. By this property, determinant of a product is product of determinants. Okay. So then, yeah, this is a product, right? A product of three matrices. So it is equal to P determinant times A determinant times P inverse determinant. Okay. A number times a number times a number. A number times a number, I can switch the number. Let me move this number here. Then I get P times P inverse times A determinant. Okay. Hey, now determinant times a determinant is equal to P times P inverse determinant by the same property. Okay. P times P inverse is identity matrix. Identity matrix determinant is equal to 1. Yeah. Determinant is a number. This number is equal to 1. Okay. So it's equal to A determinant. Yeah, we have this equation. Okay. Then the proof is done. So remember these two properties, we often use them. Okay. We often use them. Okay. This is a second topic. First topic. Now, second topic. More examples about determinants. Yeah, more examples. Topic number 2. Okay, let me show you more examples. Example 1 under topic 2. We are given A, B, C, D, E, F. These are some scalars. G, H, I. This determinant is equal to 7. We don't know what A, B, C, D, C, F, G, H, I. We don't know what those numbers are, but we know determinant is 7. Now, find this determinant A, B, C, 2D plus A, E plus B, 2F plus C, G, H, I. How to get this determinant? Now, solution. Okay, now let me simplify this determinant. Okay, now let me perform. -1 times row 1 plus row 2. -1 times row 1 add to row 2. Then put the result in row 2. Then I cancel A, B, and C in row 2. But this operation doesn't change the value of a determinant. So let me write solution here. Yeah, here. -1 times row 1 add to row 2. Then we get this determinant. This operation doesn't change the value. So this determinant is equal to this determinant. On the second row, I see that the number 2 is a common factor. I can take out the number 2. So 2 times this determinant. But this determinant is 7. So therefore, 2 times 7 is 14. Done. Yeah. So this determinant is equal to 14. This is example 1. Example 2. Example 2. Example 2. Use determinant to decide if the following vectors are linearly independent. The vectors are 4, 6, 2. Second vector is -7, 0, 7. And -3, -5, -2. Okay. Now, how to use determinant to decide whether the three vectors are linearly independent? Okay. By definition, okay, we need to solve this vector equation. if this vector equation has only zero solution, then the free vectors are linearly independent. This is the meaning of linearly independent. Okay, solve this equation. Okay, but this equation is the following matrix equation. Yeah, same equation. Yeah. X1, X2, X3. Yeah. So this vector equation has only zero solution if and only if this matrix equation has only zero solution. Okay. When this matrix equation has only zero solution, okay. Let me give a name to this equation. Equation 1. Equation 1 has only zero solution if and only if, let me give a name to this coefficient matrix, call it A. A is invertible. Do you agree? When A is invertible, I can move A to the right side and get the solution. The solution is zero. Okay, now how to see matrix A? Now how to see A is invertible? Compute determinant. If the determinant is non-zero, then A is invertible. Therefore, equation 1 has only zero solution, and therefore this vector equation has only zero solution. By definition, the free vectors are linearly independent. Now, let me compute determinant of this matrix on the next page. Now, compare. Okay, determinant of A. 4, -7, 3, 6, 0, 5, 2, 7, -2, determinant. So I put vertical lines means determinant. Okay. How to compute this determinant? I prefer to use the approach of reducing the determinant to epsilon form. I don't like expansion. Okay. Okay. Now, let me see. I first switch the first row and the third row. When I switch, add a minus sign. Second row, not change. But the first row now becomes the third row. Perform in elimination now. Okay. I use 2 as my pivot number to eliminate 6. So -3 times row 1 plus row 2. Put the result in row 2. Yeah, this operation doesn't change the value of this determinant. This determinant is a number. Okay, so it is equal to -2, 7, -2. Now, -3 times first row, add to the second row. So 0. -3 times 7, -21, add to 0. -3 times -2, 6 plus -5, so 1. Okay, now I use this number as my pivot number to eliminate this number 4. How? -2 times row 1 plus row 3, then put the result in row 3. Again, this operation doesn't change the value of a determinant. So -2 times row 1, add to row 3. So 0. -2 times 7, -14, -21. -2 times -2, 4. Then 1 here. Right, now continue to compute the determinant. Right, now this time I use -2, this number, to eliminate this number. How? -1 times row 2 plus row 3. Put the result in row 3. Yeah. This operation doesn't change the value. -2, 7, -2, 0, 21, 1. Then 0, 0, 0, determinant. Now, this determinant is an upper triangular determinant. Determinant of upper triangular matrix is equal to the product of the main diagonal entries. 2 times -21 times 0. So 0. Oh, determinant of matrix A is 0. Therefore, A is singular. Singular means matrix A is not invertible. Okay. All right. So go back to this equation. Matrix A is singular. This equation has non-zero solutions. Non-zero solutions because one of the unknowns is a free unknown. One of the unknowns is a free unknown. Yeah, free. When the linear system has a free unknown, the linear system has infinite many solutions. So therefore, conclusion is this vector equation has non-zero solution. Therefore, these three vectors are linearly dependent. Okay. So conclusion. Conclusion. The three vectors are linearly dependent, not independent. Done. Yeah. So in this example, we see that we can use determinant to determine some given vectors are linearly dependent or independent. Yeah. Okay, this is topic 2. What is topic 3 today? Oh, determinants have some applications. Now let me show you 2 applications. This is section 3.3. 3.3. Okay. Some applications about determinant. Topic 3. Some applications. All right. Number one, we can use determinant to compute solution of a linear system. Topic one, the first application is Cramer's rule. Cramer's rule. Okay. Cramer's rule. Yeah. Okay. It is a theorem. You can find this theorem in the book. Okay. Suppose A is a square matrix, and the square matrix is invertible. Okay. Invertible. Therefore, invertible. Therefore, determinant of A non-zero. Okay, non-zero. Okay. Okay, then suppose A is invertible. Then this linear system has a unique solution. Okay. When A is invertible, the linear system has just one solution. The solution is A inverse times B. Okay, times B. Okay. All right. The ith entry of the solution is given by the following formula. Xi, yeah, X is a vector of the unknowns. The ith unknown is equal to determinant of A, I, B. I will tell you what is capital I, B means. Determinant of AIB over determinant of A, because determinant of A is non-zero. Yeah, this number can appear in the denominator. Okay. All right, now let me explain what is AIB. Okay, where AIB is the matrix obtained from matrix A by replacing the ith column of A by vector B. Say for example, A, matrix A, first column A1, second column A2. The ith column is AI, and so on. And then AIB, this notation means this matrix replace column I by the right hand side B. Yeah. This is AIB. Then after we get AIB, compute determinant. Determinant of AIB over determinant of A is Xi, the ith entry of the solution of this linear system. Okay, now let me show you one example about Cramer's rule. Cramer's rule. Okay, take a look at one example. Example 1. Use Cramer's rule to find the second entry of the solution of the linear system. Yeah, 3x1 minus is 6. Negative 5x1 plus 4x2 is 8. Yeah. In this example, we don't need x1. We only need x2. What is x2? Okay. Now, to answer the question, to use Cramer's rule, let me write the linear system in matrix equation. Okay. In matrix equation, matrix equation is this. In matrix equation, okay, the linear system, the system is coefficient matrix 3, -2, -5, 4, then times the unknown vector x1, x2, and then right hand side 6, 8. Yeah, this is the matrix equation of the linear system, where A, capital A, is this matrix. B is this vector. Okay, now I can use, after I write the linear system in matrix equation, I can use Cramer's rule. Okay, by Cramer's rule, the second entry of the solution is x2 is equal to determinant of A to B over determinant of A. This is a Cramer's rule. Okay, now let me compare matrix determinant of A first. Okay, determinant of A. A is 2 by 2, so easy to get the determinant. 2 by 2 determinant is equal to product of the main diagonal entries, 3 times 4, minus product of the anti-diagonal entries. So we get 12. -5 times 2, 10, minus 10. It is 2. So this number is equal to 2. Now, I compare determinant of A to B. Okay, first, what is A to B? Okay, A to B, AIB is the matrix obtained from the original matrix by replacing column I of A by the right side. Okay, now A to B is, this is A. Now replace column 2 by right side. 6, 8, yeah. This is A to B. Now compare determinant of A to B. Yeah. Again, 2 by 2 determinant. So it is product of 3 times A minus -5 times 6. This is a plus 30 or 54. So this number is 54. 54 divided by 2, 27. 27. So the answer is the second entry of the solution of this linear system is 27. 27. Yeah, this is a Cramer's rule. Yeah. We can use determinant to find some entries of the solution of a linear system. Yeah, Cramer's rule. Yeah. This is our first application. Now, second application, we can use determinants to compute the inverse of a matrix. Yeah. Okay, second application, B. Use determinants to compute A inverse. Okay, A inverse. Okay. All right. The formula is okay. Form matrix C first. First entry is C11. Okay. Recall that Cij, I mean this number. I plus J. Determinant capital A I J. Yeah. We call this number I J cofactor. Different name. Okay. Yeah. So matrix C is a matrix of cofactors. Form the matrix of cofactors. C11, C12, C1n, C21, C22, C2n, and so on. Cn1, Cn2, Cnn. Yeah, this is the matrix of cofactors. The matrix of cofactors. Then it can be proved that matrix A times matrix of cofactor, it is a matrix. It is determinant of A, it is a number, times identity matrix. Yeah. The size of this identity matrix is n by n. Okay, n by n. Yeah. So how to find the inverse of A? Okay. If I don't know that the determinant is 0 or non-zero, if A determinant is non-zero, namely A has inverse. Okay. If this number non-zero, then I can move this number to the left side. Then I move this number to the left side. Then A times 1 over this number times C is equal to R. Yeah. Matrix A times this matrix is 1. Therefore, A inverse is 1 over this number. Now I miss a transpose here. Yeah, A times C, not A times C, but A times C transpose is equal to this number times I. When this number non-zero, I move this number to the left side to get this equation. So yeah, I miss transpose. Yeah, transpose. Yeah. So therefore, this matrix is the inverse of A. This formula is the formula about A inverse by determinants. Yeah, cofactor is a determinant. Yeah. Okay. Now let me show you one example about this formula. Yeah. Example. Example 2. Example 2. Okay. Find the inverse of this matrix. We learned one approach to find the inverse of a matrix before, right? How to find the inverse of this matrix from augmented matrix. Then reduce A to identity matrix. Then suppose that I becomes some matrix C. Then C. Then this guy is A inverse. Okay. Now, here in this example, I don't use this approach to find A inverse, but use determinant. Okay, the formula is here. Formula is here. Okay, okay. Now let me compare A determinant first. Solution. Solution. Let me compare determinant of A. 2, 1, 3, 1, negative 1, 1, 1, 4, negative 2 determinant. I prefer to use elimination, reduce the determinant to epsilon form. Okay, now let me switch the first 2 rows. When I do switching, add a minus sign. The third row not change. Now perform elimination. Negative 2 times row 1 add to row 2. This operation doesn't change the value of the determinant. 0, negative 2 times row 1, negative 2. Negative 2. Yeah. Then negative 1 times row 1 add to row 3. 0, negative 1, 5, negative 1, negative 3. Okay, now continue. Okay, continue the elimination. Now, negative. I want to use number 3 to eliminate number 5. Then negative 5 over 3 times row 2 plus row 3. Then put the result in row 3. Yeah, I use this operation to get rid of the number 5. 1, negative 1, 1, 0, 3, 1. Okay, now negative 5 over 3 times number 3, add to 5, 0. Negative 5 over 3 times 1, add to negative 3. Yeah, What is this number? This number is negative 14/3. Yeah. Okay. Now this is an upper triangular determinant. The determinant is equal to the product of the main diagonal entries. So 1 times 3 times negative 14/3. So this is a positive 14. Okay, yeah, this is a determinant of A. Okay, now determinant of A, I got it. Now determine the matrix C. Wow, the matrix C, we need to compute the cofactors. Very tedious. Yeah, this approach is tedious. Now, next page. Let me compute the cofactors. C11 first. Yeah. Yeah, C11. Okay. C11 by formula, -1, 1 plus 1. Then determinant of capital A11. So this is a -1 to 2, positive. So A11. What is A11? Go back to the matrix A. Yeah, matrix A. A11, that means that delete row 1, delete column 1. Yeah, this part is capital A11. So it is -1, 1, 4, -2. Yeah, so 2 by 2 determinant, it is -1 times -2 minus 4 times 1. So this is a 2 minus 4. -2. Yeah. A11, -2. And similarly, A12 is -1, 1 plus 2 determinant of A12. Okay. In a similar way, we get the number is 3. C13, the number is 5. C21, 14. C22, very tedious, this approach. So I prefer to form augmented matrix, then reduce A to I. I prefer this approach. Okay. C22, C3.3, -7. C31, 4. C32, 1. C33, -3. So therefore, the matrix of cofactors is this matrix C11, -2, 1, 2, number 3, 1, 3, 5, 2, 1, 14, 2, 2, 2, 7, 2, 3, and then 3, 1. Yeah. Hey, now by formula, A inverse is equal to this number times C transpose. So conclusion is, so A inverse is C transpose. Okay. Determinant of A, I got it number 14. So 14. Then times take transpose on C. Let me draw the main diagonal line. Main diagonal line. Then rotate the matrix in this line. I get -2, 3, 5. First column, second column. 4, 1. Yeah. and multiply this number to all the entries. Then I get 1/14 multiply -2, -1/7. Then this number times 14, 1. This number times 4, 2, 7. 3, 14. This number times this, -1/2. This number times 1, 14. This number times 5, 5/14. This number times this, -1/2. This number times this, -3/14. Yeah. So that, yeah. This matrix is A inverse. This is about this formula. I stop here. Then on Thursday, we turn to study chapter 5. Chapter 5 is about eigenvalues and eigenvectors of square matrix.